then I will upload to YouTube, and then you will get a link to the last lecture, because I don't have like pen and paper to explain you numbers and how we calculate them. That would be that for you easier if you have video recording.
Recording in progress.
Great. So then let us begin slowly. So far, we discussed 3 out of 4 main steps of the insulin production. So namely fermentation, primary recovery, and then what I call chemistry, reaction section. And we see that actually fermentation doesn't take that much of effort. So, and that's due to actually, contrary to a very popular belief, people say, okay, there must be, optimization in the fermentation. Usually optimization is required, optimizations are required everywhere in the downstream. Of course, the cells, the bacteria, E. coli, they must be optimized and optimal conditions. But you see how many extra degrees of freedom are involved here. Yeah. So you can think about every and each reactor here as a big machine, as a big black box, where you have to have numerous variables like concentration, time, temperature, concentrations. Yeah, all in all. Non-additives, you can also change pH and things like this, and then this all will change the yields, and of course will change the number of byproducts you have to get rid of. So last time we have arrived at this place, so we have finished all the chemistry, and now let me skip all these reaction sections, so you see that how many chemistry is involved. What we have achieved, we have finally disconnected C-peptide out of from the proinsulin. So we have insulin in a correct folding state. We'll speak about folding this lecture a little bit, and we basically have to purify it. How it's purified. So we are not going to, of course, discuss details, but as you can imagine, purification of proteins out of low molecular weight compounds going to be done by chromatography. That's a very, very natural type of separation technique. So again, here we are talking about column volumes. So we are not talking about retention times. That's, as I told you last time, is very common. So we're talking about approximately 8 column volumes to get the product. We use a stationary phase, which is aqueous. So we consume by this quite some amount of water, and at the same time we dilute. That was maybe more important. We dilute our batch. So liquid volume is still quite high. You remember we had like the hundreds of liters in this range at some chemical steps in the reaction section. Now we are almost at 2,000 liters. It's quite some amount, and that of course suggests that at some point we have to reduce this amount, because as we remember, all fine downstream purification process like chromatography, they have a very, very low throughput compared to the chemical reaction. For example, you can scale up your chemical autoclave, and you can basically implement a chemical reaction in pretty large vessel. What happens here, you have to pump basically literally through a huge amount of liquids, and you have the risk of damaging your column. You have the risk of absorbing something what can hardly be eluted from the column, things like this. And of course, your stationary phase gets degraded with time. So you would like, and and basically the throughput itself is very low because you have to apply pressure, to pump a certain amount of liquid through. And that's why you would like to keep volume quite low. And that's why we have a series of chromatography units, and after each column, we have, again, a very common to us process, which is called diafiltration. So we combine dialysis and filtration here. So we filter through a dialysis membrane. We don't wait until low molecular weight compounds diffuse through the membrane, but we help them by applying pressure. So we create a pressure gradient along the membrane. And the membrane is, as we many times discussed, only permeable towards low molecular weight compounds. So all the protein or all high molecular weight compounds with a specific cutoff remain in the solution, and water also goes away. So by doing this, we actually not only purifying, but we also reduce the volume. Yeah? And after this, two purification units and two diafiltration, what we have is, by a factor of 10, reduction in volume. Now we have approximately 880 liters, and we have approximately 13 kilograms of insulin. Filtration, as we discussed many times, quite efficient. We don't lose product. We actually lose water and low molecular weight compounds. Product remains inside, and then the liquid phase, and the yield is usually quite high. And finally, we are lucky that insulin forms crystals when we add zinc-containing compounds. In this particular scheme, we use zinc chloride and ammonium acetate as a pH buffering system. So we have basically an industrial crystallizer, and we have literally crystals of zinc complex of insulin. So then we have to mechanically separate this. Standard things like basket centrifugation is used. Then you basically have crystals and a mother liquor, which contains only zinc, excessive zinc, salts, and some amount of acetic acid, which you also add at this point. Basically, you have your solid product, step recovery 90%. Again, very typical. You have many places where you can lose your crystals, and some amount of insulin remains in the solution. So as you remember, all the phase boundary lines, equilibrium lines are not, unfortunately, approaching 100% axis position, and you always thermodynamically are limited, and that's exactly the case here. So crystallize, some amount of insulin stays in the solution. And finally, freeze drying, because you have that product, you just remove water by subliming this water out. So you freeze your semi-solid product, and then you basically apply a vacuum. Under vacuum, water remains solid, and then at the same time, a vapor pressure is kept over the water of the crystals with the ice low, so that's why it can sublime from the chamber. This pretty energy consuming process. And then finally, at the end of all purification steps, you have 11.5 kilos per batch. Yeah, so we run 160 batches, if I'm not mistaken, 180, 160 batches, I think, per year, working around the clock. So it takes us 48 hours to get one batch through the entire scheme. 11.5 kilos is a significant amount. Well, we'll see later what are the selling prices and then you can judge, and then you can also evaluate basically macroeconomical, so to speak, um, values and figures of this process. So what we can say around about the final yield, the total recovery yield. Yeah. So if we have if we were able to separate all the pro-insulin and convert it with 100% yield to insulin, we would get plus 68%, approximately plus 70% on top of all what we get at the end of the real scheme. So our overall recovery yield is approximately 32%. So 1/3 of the insulin of all the propi molecules which E. coli have generated and stored in the inclusion bodies are recovered at the end at this point. Okay. Do you have questions to this scheme? You can freely unmute yourself and pose a question. Seems to be not the case. Let us then maybe take a look at the cost breakdown for the production. So what we have, 11.5 kilos of insulin, main product, MP. Let us take a look first what sort of bulk materials we require, because we're chemical engineers, so we begin to speak in terms of chemicals and then later consumables we require for the process. And you are quite surprised, I think, how much water you require. So take a look. To produce 1 kilogram of insulin, we require over 5 metric tons of water. Of course, this water will be purified. Yeah. So never believe those who say, you know, to produce 1 kilo of meat, you require, 6,000 liters of water. And so what? Your water doesn't disappear then later on. Yeah. It has to be purified. We do need energy. That's all correct. But that's important to understand. It will be purified and will be, of course, reused to a certain extent. And we have a great purification scheme in our nature. Yeah, water gets evaporated, goes down as a rain. Yeah, rain is purified water, by the way. What else? Sodium hydroxide, phosphoric acid, and of course a very, very special type of water, which is listed as a separate item here. It's much larger amount, but let us speak in terms of overall water later on. Ammonia, which you require air, quite some amount of air, and so on and so forth. So you see that basically you require compounds which are solvents. If this process were an organic chemistry process, you produce a drug, yeah, in non-aqueous medium, then instead of water, you would get pretty much the same numbers for a non-organic, non-aqueous solvent, like I don't know, toluene, for example, or something like this. Yeah, so we always have a big amount of medium we require to process. So we never work at very concentrated, or very seldom work with very, very concentrated solutions. And then you see mainly things like to set pH, to convert proteins into a specific conformation, things like this. I have more of course formic acids, because you remember at one stage we had to switch to non-aqueous medium because one of the chemical reactions can only run in 70% formic acid. And urea, of course, biotech requires a lot of urea and many other things. All in all, you require almost 46 tons of chemicals to produce 1 kilo of insulin. Impressive number, 46 tons, yes, of chemicals. Again, don't think about this, all chemicals are hazardous chemicals which necessarily kill all the life in the over the globe. That's not correct. So most of them are required, and most of them are quite unproblematic. If you see that sodium chloride, for example, we consume quite some amount of acetic acid. It's all relatively non-toxic chemicals. But the mass, what would have to impress you is not the amount of chemicals, but the amount of mass you have to move. Yeah, because chemical engineers, they think about mass transfer. And I don't know whether you have thought about this already or not. Everything every and each kilo we move through membrane, through any unit actually, cost us energy. Yeah, nothing happens on its own. And of course, we are not considering energy balance for this calculation can be much more complex. But you have to move 46 tons of weight to get 1 kilo of something valuable. So this something valuable should be very, very valuable, and the selling price should be high to make the process profitable. We'll speak about this in a second. How we identify a process which is so-called bottleneck? Well, I mean, we have to identify a process which has which has a shortest processing time. Yes, so that's basically all, and then we basically arrange them. What is the processing time required for each and every step? And then we see that the process with the idle time, the highest idle time we have is this refalling process and diafiltration. So we treat this too because we concentrate and we send the back solution over here. Maximum number of batches is determined by this. What do we mean? We basically have to think about this picture. No matter how fast all the steps in your scheme are, if you have a step which is a limiting step, yeah, which is a bottleneck, then the overall speed or overall rate of your process will be determined by this particular step. And that's what we have to basically quite well understand. No matter where it is, it can be at the beginning, it can be very end, in the middle of the process. So you can be fast here, you can be also fast here, but you have to wait. Occupancy time is 45 hours is the minimum possible time between two batches. Yeah, that's why we actually can run only one batch per 48 hours. That's the number which determines our time and our schedule. 160 batches per year makes sense. Yeah, so every third day we start a new batch. 160 batches here. Now let us take a look at the numbers. So it is, of course, in prices not to 2022, 2005. I just taking this from the software which goes along with the book I just recommended you on the process last time. I don't really care about how accurate numbers are. I just want to explain what these numbers and figures mean. Let us do a little bit of calculations together. Total capital investment. What do you think this is? The very first line in the table. Total capital investment. What do you think this number tells us?
The total amount of money that we required for
For?
yeah for the plant.
For the plant.
Yeah.
To buy basically parts, to assemble, maybe
Equipment.
building as well, land and things like this.
Yeah, yes. Yeah.
Perfect. Total capital investment is clear. So if you are to invest in the insulin production, so basically this a minimal amount of money which you require to start basically to build up the plant. Capital investment charged to this project is 189 million dollars. What this is?
I think the first one was what we planned, that this might be the capital cost, but the second one is the charge that is happening really, that we have paid.
Yeah, exactly. So there will be always a difference. So because your planning is not perfect, so you see that some solutions, for example, you don't have enough water, purified water, you have to build up an extra water purification facility. Or then suddenly, or you anticipate, for example, that regulations and norms will be changed regarding the wastewater, and then you say, okay, I don't care that much. Let me invest, say, 5 million into waste treatment equipment, and so on and so forth. Okay, so we or you as an investor have spent 189 million euros, and plant is here. Just you staying in front of the plant is ready to operate. What are the operating costs? How we understand this number? 106 million euros per year.
This is the amount that we need to run the plant. I mean, we need the raw materials. We need to pay the money to the workers, to the
labor cost. Okay, labor costs, consumables. Yeah. I included chemicals as well.
Yes, I think so.
Chemicals, consumables, labor. We're gonna see in a second, yeah, the cost breakdown for this particular amount. That's very interesting to see.
The utility cost?
Yeah. Gonna show you the next slide. What is production rate? Is how many batches we can process per year, 160, and we multiply 160 by 11.5. Yeah, that's how we arrive at the production rate per year. So this is amount of product in kilograms, main product, you get after the freeze dryer. It's not that much. It's less than 2 metric tons. That's what you get basically in hand in your stock after the year. Unit production costs. What this number is? Unit production costs.
I think from the units, it is clear that it is the amount of the unit that we need to produce 1 kg of our product.
So we require 46 tons of chemicals, of various chemicals, to produce 1 kg of main product, and we require approximately $60,000 to produce 1 kilogram of insulin.
Yes.
So definitely this number, yeah, 60,000, without inflation, without all this macroeconomical situation and all these things. So this number determines you the lowest boundary for the selling price. Yeah, so you can't really sell, if you want to be profitable, insulin at the price lower than approximately 60,000 euros per kilo. Good, that's all quite clear. Total revenues, what this number tells us and how we calculate this.
The total amount of money that we are getting after the production.
And you tell me what is the selling price then?
We will just, so our production is 1803 kg per year.
1803 kg per year.
Yeah, so we will just divide this by this.
Exactly. How we arrive at this number?
We will multiply 1803 by by 365.
Not really.
58,000.
Oh, by 105. No.
1803 multiplied by 58,000 unit production cost.
Not really. No. Total revenues, what this number tells us is how much money we get when we sell all the product we produced in 1 year. So we have to have a selling price here. Can you
Yes,
tell?
we can multiply 1803, the amount of the product, with the
Yeah.
per kg amount of the. No, I don't know.
So in this example, we assume that the selling price is $100 per gram. That's a very reasonable amount, yeah? So it's a reasonable price. So if you assume that you have $100 per each when you sell each gram, then you have $100,000 when you sell 1 kg, right?
Yes.
And this is the number which you get with the rounding errors, but all in all, so you can get as total revenues $180 million per year. Okay, that's clear. What then this gross margin is often displayed in percent. What this number can tell us, gross margin.
Is it the total revenues by operating cost by total revenue?
Almost. So you have total revenues. Now you basically literally have 180 million euros on your bank account. Of course, you have spent some amount. How much did you spend? We're not talking about now capital investment. We're just talking about operating costs. So to produce
$100,000 per year.
Exactly.
We pay and we earn $180,000 per year.
Exactly. So
and that number is their difference between operating costs and total revenues, which will be $75,000 per year. And when we divide it by total revenues, it will be 1.45%.
Yeah, 41%.
That's the margin. That's our our distance from our margin between how we pay and how we earn, how much we earn.
Exactly. So to calculate this, so it's called gross profit margin. Yeah. So we of course have to take into account how much we get and how much we spend. So we take 180 million as our total revenues. We have to subtract some amount. In general, what we subtract is called COGS, cost of goods sold. Yeah, cost of goods sold. In our basically example, this amount is operating cost, all operating costs. Then we subtract from 180 million this amount, and we divide this by total revenues. Then we have this gross margin, yeah, in percent. What does this number tells us? It basically tells us what is a fraction of money which are left over, yeah, from all production sales, yeah, we can say. Because you have, of course, spent some amount, quite some amount from this sum to keep your production running, to keep your operation process running. That's clear. 48%, 41%, almost 42%. Return on investment. Now, investor comes and tells you, okay, I mean, you make money with your plant. How about return on investment? How we calculate this and what this number tells us?
I think this is the total revenues that we generate after per year. and we compare it with the 188 million that we have already
Yeah.
charged for this project,
Mhm.
for the project.
So
And
what you
then
say? Yeah, please.
Yes,
So do we want to compare this total revenues with this number?
yes.
But we of course have to spend time to operate the plant.
We have to, I think we have to subtract the operating
Exactly.
cost. First, the amount that remains, the only profit that we have now.
Exactly.
We
Exactly.
compare that with the capital cost.
Yeah. So the logic behind this return on investment is very, very simple. So you get total revenues, you subtract all the operating costs. This is the money you have. You basically have this free cash, so to speak, right? And then if you give back to your investor all the cash you generated in 1 year, then that's amount of money in percentage divided. So basically 180 minus 105. This is amount of cash you have after the financing year is over, and then you divided this by the capital investment, actual capital investments for your project. So you within 1 year can generate 40% of the money investor has invested in your production plant. Okay.
Yeah.
You have paid labor costs, consumables, chemicals, all is taken care of. And then, of course, payback time is how many years you have to operate to generate as much cash as your investor has put into your business. 2.5 years is a very, very actually, it's extremely fast time in this example. Usually, it depends very much on the sector. It can be also 5 years, it can be 20 years. Long if you invest in something very classical. Here, of course, why this number is high, because your total revenues exceed operating costs by quite some amount. So your gross margin is over 40%. Usually, it's only possible when you do it in biotech and towards pharma. When it comes to food, then you have, of course, governmental regulations, and then you can't really, put prices as high as you want. And you, of course, have also many competitors. So the gross margin is not going to exceed, say, 10% or something like this. Yeah. So of course, if it is 10%, not 40, then this payback time increases drastically. Yeah. And the investor has to play along and then has to understand that you have production, which and then of course inflation comes on top, and then maintenance and all these things, unexpected maintenance, because usual maintenance is integrated into operating costs. You have questions to the calculation. So it's a very, very standard thing. If you then later on want to invest in something, these are the numbers and figures which you may or certainly will take a look at first. If not, then let us take a look at the annual.
One question in the chat.
Let's see this. As a rule of thumb, what would be considered as max payback time for such a chemical wire? Industrial available. For biotech, I would say within 3 years. I would say 3, 4, 5 years. I would say that's a very realistic. Time has, sped up a lot. Yeah, so it's difficult now to convince investors to play along, because we never know. We will discuss this. I have a couple of examples, nice examples. For example, you say, okay, I want to have it's not a plan, but I'm in a service. I read DNA sequences. I have a very brand new machine, and I'm going to offer this, as a service. And then suddenly new technology comes, And if your payback time is 2 to say 5 years, then this technology wouldn't doesn't do any that much harm to your business. Yeah, so at least investor gets his or her money back. But on a long time basis, when you say, okay, I have 10 years, and then suddenly after 2 to 3 years, so you still have to pay your investor a lot of money, and the new technology comes, and then it is already in a stage that it can be industrially applied. Then this new technology drives the selling price down. Then of course you are no longer able to compete with the companies which utilize this new technology. And then of course this payback time increases and increases. At some point the cross margin is going to be very, very high. Return on investment will be very, very low, and then the payback time is also low. That is why nowadays I would say 2 to 5 years. Okay.
Sir, I have one question.
Yeah, sure.
The investors that they have invested their money first, so now they're getting the money back. So when they're getting the profit for the money that they have invested, they're just getting their money back, as we have studied here. So when they are getting the profit on the money that they have invested.
Well, it depends. It depends. They may, for example, wait a few years, and they say, okay, I mean, you need to start your plant, and then you initiate all these things, and then you have to establish market channels, for example, things like this. So we give you say 3 years of the, so to say, of the period you don't need to pay us anything. Investors can also say, we don't really care because we are now shareholders. So basically what they do, they invest money. They don't ask you to pay money back, but they own part of the company, of your company. You can be CEO, you can say own, say, I don't know, say 70% of the business, but remaining, I mean, all the co-investors, yeah? So they all, for example, have 70% of the business, and then 30% belongs to investor. And then of course, later, when your plan generates profit, then investor, depending on the agreements, has right to withdraw 30% of the not total revenues, but the margin, yeah. So total revenues minus the operating costs from the business. Or it depends very much, yeah. So maybe they have, I mean, a seed like CEO, so basically a person who is working with you together with CEO, and basically they have an influence, like certain influence on you, and they say, okay, like reinvest this money, we don't take it, we don't take our 30%, but like let us buy this business, or like buy this competitor, or invest this money in something else, or like renew the plans to be to operate at the newest technology possible level, things like this. It's a very, very is basically agreed within the CEO and all the investors and all the business owners.
Yes, thank you.
Let us then take. Here we go. Yeah, so this is that's very interesting. I think it's very instructive to take a look at these numbers. How much? So we spent for 106 million euros for annually for operating costs. Let us take a look what is the cost breakdown. For consumables and raw materials, we spend 34 and almost 30%. It's a very, very, actually for biotech is very reasonable numbers. So raw materials should not exceed 50% for sure. labor depends, of course, on the region. You see, it contributes like less than 10%. And that's important to keep this labor-dependent costs very low. And that is why people speak about, big data and automatization and things like this, because of course labor is very, very expensive. Facility dependent. What is facility dependent? What do you think? This 20% which come to that operating cost, facility dependent. What can be?
Bioreal, I mean, all your equipments.
Mm-hmm.
Is that it?
Yeah, cleaning,
Okay.
Maintenance as well, and basically cleaning of the entire building and reconstruction, renovations, plant things. So consumables, 34%, coming back to consumables and to raw materials. When it comes to biotech, is very, very, actually, don't be surprised. Consumables cost a lot of money because in the supply chain, you are never along between the raw materials and the final product. Of course, you need many firms which supply you consumables, and as you see here, these are not just consumable standard things, but it's like stationary freezers which are designed to be specifically tailored for insulin absorption, for example, and things like this. So specific filters, filters for air, filters for gases. This all costs money, and of course you see that the markets of consumables and to a large extent of raw materials, because all in all is over 60%. Yeah, so 2/3 of all your operating costs are coming from these consumables and raw materials. Basically dictate the final price. So whether you can maintain this or not. Labor does not. Yeah, so usually we are not as business owners of a business consumed about labor dependent costs. Waste treatments, this thing increases a little bit, and that's very destructive as well. Lab and quality control usually is not that much. Yeah, so if the process is optimized, you usually don't spend much money on the quality control. Of course, raw materials have to be controlled and the final product as well, but is usually not like R&D activities. You don't need to develop something what costs you time and money. Is just the very standard chemicals and very standard protocols which you apply to quantify, for example, amount of insulin, I don't know, residual water, pH, things like this. So it's not that much. The second thing I want you to take a look are, if we take a look at the operating, again, this $105 million you spend per year, if you just see at which section of your production scheme you need what amount of money. Again, especially the very, very last column, these absolute numbers tells us a lot. Fermentation and primary recovery are usually the steps where you spend very little amount of money when compared to the final purification. That is why if you are an engineer asked to optimize something in the process, of course, you would first of all take a look in the focal point of your optimization would be then the very last two sections, namely reactions and final purification. Of course, here even 1% increase in the final yield means a lot, yeah, because your selling prices is quite high, and of course then you also spend quite some money. In absolute amount is like is 80, oh yeah, boy, 85% 15%, yeah, 15% just for fermentation and primary recovery. That's a lot. So if you are a couple of startups also on campus here, so they use fermentation, primary recovery, but not final purification because they're just fine. I just don't want to name them, but you can easily find out. Which use, for example, bacteria to produce valuable things like macromolecules or oils, things like this. If you analyze the business and you see that there is no need to perform chemical reactions and the final purification is not dead labors, it means that basically the amount of money you require is not that high. So the operating costs will not be that high if you just need fermentation, say primary recovery and some simplistic final purification. That's maybe will help you later to analyze at least biotech businesses which are based on fermentation and delivery as a core process where we utilize organisms to produce pro-insulin or pro-product, so to speak. That's, I think, would be the last table I want you to take a look. It lists raw materials costs as a percentage of the annual operating costs. And you see, surprisingly, that you spent 14, let us sum up, 14 plus 17 plus 15, yeah, 40, it's like 40 something, 46, yeah, 46%, so half of the costs, operating costs, are coming from very simple chemicals, urea, water. So now I combine basically water for injection and for all the steps, but exclude standard water for cooling, for example, and phosphoric acid. That's quite interesting. And that's actually a good sign because you use chemicals which are very, very inexpensive. Take a look at the annual amount in kilos and unit costs. Yeah, so phosphoric acid, $1 per kilo. Sodium hydroxide, 0.5. Water, 0.1. Usually when, again, I think I mentioned this, very often, oh guys, I mean, but this process requires water. Water for industrial uses are very inexpensive. So when you compare price of water to chemicals, usually they are much more expensive. So this is the cheapest thing you get. So if you use a lot of water, if regardless, of environmental aspects, you are not driving up the price a lot. Of course, water without any special treatments, like for cooling, for example, is even cheaper. Ammonia, I think, yeah, 0.7 or 0.6 glucose is even, yeah, so it's comparable to 1 kilogram of glucose, yeah, is comparable, is 6 times more expensive than 1 kilogram of water, purified water. It's impressive comparison, to be honest. What else? Nothing big. Yeah, formic acid, again, only because of this issue with non-aqueous medium for one reaction, almost 10%. So how much you spend for all chemicals? Let me take a look. Annual costs, yeah, 30,000. 30 million dollars out of $105 million. Approximately 1/3 goes, 29%. As this diagram tells, goes for chemicals. Do you have questions? That's basically the way how you analyze and you see what are the bottlenecks. Yes, if people say, okay, increase our salaries by 5%. You see this cost breakdown. Doesn't change much. But if all your suppliers suddenly tell, okay, all the chromatographical stationary phases are now going to cost 20% more because you consume them a lot. Yeah, so this will increase this segment quite significantly, and then of course it will drive up your overall costs. The same is applicable for raw materials. This analysis where you can easily do if you have such figures for operating costs. Of course, then marketing department will of course tell you what are the reasonable selling price, how many competitors you have on the market, and what is the structure of the market. Of course, this $100 per gram is not the price in the drug shop. Yeah, so you basically sell raw material. It has to be formulated. It has to be basically repackaged and labeled and packaged and then supplied to the hospital, for example. Then there is an extra step and there is an extra margin. Question whether you want to do it or not. Yeah, maybe you just sell your insulin as a bulk powder because you don't want. It does not, increase your. Doesn't influence that much your profits or your profitability of the firm a lot if you just introduce an extra step of getting this into the test tubes label and so on. Yeah, that's basically brings me to the end of the insulin story. Do you have questions?
Professor, did we include the energy costs in this because it shows utilities as 0?
Mm-hmm. So basically, we included energy costs here. That's what I forgot to mention. This 20%, usually energy costs in biotech are not that high. The reason, you can guess the reason, yeah? So you usually keep temperatures quite low. Maybe 40 is the highest temperature you use for instance production. This is the energy cost I include in facility dependent costs in this case. That's true. Something else? Depreciation as well, yeah? So facility dependent depreciation. Your equipment gets older. And then of course, at some point, you have to buy basically new pieces of equipment. You just say, okay, it doesn't matter whether it works or not. Yeah, so if depreciation period is over, say 5, 7, 10 years, depending on the equipment, then of course you have to be on the safe side because, for example, company, your supplier does not support this type of equipment anymore. Yeah, so service engineer cannot come to you to repair this equipment, and that's all this idle time costs you money. Yeah, so if you stop your process for 2 days, then you basically lose $100 per gram multiplied by 12 or by 11 by 11.5 multiplied by 1,000. That's how much money you lose if your process is stopped for 2 days as revenue. Yeah, so depreciation as well is over here. Maintenance as well. Then, since we have half an hour more, I have a couple of slides which I want basically does not it's not connected that much to the topics we discussed before. I just came across of Forbes article on 5 biggest trends in 2022, and I like the classification. Maybe I can add something on top. So the article basically sees 5 major trends in 2022 in biotech, and I think it's quite interesting to maybe just discuss them shortly. Personalized medicine, agricultural biotechnology, pharmaceutical testing faster and faster approval of medicines, environmental, so they separate agriculture, environmental biotechnology, and artificial meat. What do you think this personalized medicine is about? How do you understand when we speak about personalized medicine? There are many startups now all the world which aim at developing solutions for personalized medicine. What this personalized medicine is about. And why our current medicine is not personalized that much. Because doctor basically speaks to you personally, yeah. So he or she does not invite 9 people to have a group of 10 and then speak to this group. Doctor speaks to you personal, so they personal. You take a look at your personal case. In this sense, it is personalized. But what do we then aim at when we want to develop personalized medicine solutions?
Is it medicine that is catered to your genes, like your DNA?
Yeah, exactly. That happens. That actually happens. This all discussions because the cost to read your genome goes actually drastically down. I'll show you a picture. So basically what we speak about is we are talking about all possible analysis we can do with your body, blood, DNA, whatever other things. And then we take markers which are individual to you. Now you can say, okay, we also analyze urine, yeah? So you, for example, measure pH. This is your individual value. And then depending on the level, doctor can, okay, so, okay, you have oxalates or something like this. Maybe something doesn't work in your body properly and so on. This is not personalized medicine. Personalized medicine is basically treats all the data you get also online. And that's where the smart device is going to play a big role. Yeah, some of you have now 24/7 or are 24/7 connected, for example, to smartwatch. Smartwatch can accumulate a lot of data. These data are so far not available to your doctors. What they do so-called point measurements. Blood pressure, you just go to a doctor. I always have high blood pressure because I always late to doctor's appointments. Yeah, see, I was Professor Grieco, why your blood pressure is so high? So I have a very stressful job. It's a joke, yeah, of course. But at the end, what the doctors see in terms of data are just less than 1% of entire data we can accumulate, generate, and store. So first pillar of this personalized future medicine, if you want, is of course accumulation and being able to collect this data, being able to store this data, being able to represent this data, because for example, your smartwatch measures all the skin temperature. So we have to basically convert this or correct this temperature into the body temperature because the skin temperature is lower than the body temperature, yeah, and so on and so forth. And then a big and important pillar is DNA analysis. So we do not read the entire DNA sequence, but we read so-called markers. And based on these markers, we can decide. And decisions can be very different. For example, what? For example, you have a higher risk of this Alzheimer's disease. Yes, it's Alzheimer's decrease, I think, in English. I'm not sure exactly about pronunciation. So it's like when you have difficulty in remembering like recent events. And this is a big thing because we don't have this medicine, but we have a scientific proof that if you live a healthy lifestyle, then you can delay this Alzheimer's disease by say 10 or 15 years. And that can be also based on the DNA analysis. So the doctor now doesn't tell you DNA, does not basically make his or her decisions based on DNA, but in the future that's going to be. So the main thing is accumulation of data, and depending on the makeup of your DNA. So how much DNA reading of a DNA of a human costs now? Do you know? I mean, you have slides, of course, you can take a look at the next slide. But if you are to guess, how much would you say one analysis of your DNA would cost?
$500.
Yeah, $500 to $600. That's exactly. So it's a routine analysis, and if you take a look at the cost per human genome, and you compare this from 2001 2003, where this big human genome project had been initiated in the States. So you see the very fast individual readings, they costed, note here's a log scale, yeah, costed like 100,000, like 100,000, like $1 million per one genome. What this Moore's law is, yeah, from 2006 2007, yeah, technologies were developed a little bit earlier. Then you see a massive and then very big drop in prices and cost per human genome. They are much lower than so-called Moore's law predicts. What does Moore's law actually predicts? Why the line is drawn here, which corresponds to so-called Moore's law? What is this? It's something coming from IT, from the world of computers, Thomas, Moore's law. And all the cores, all the processors we use, they by Moore's law very precisely. What this all about? It predicts how rapidly amount of transistors, or how rapidly your computational power increases. So the Moore's law tells that the computational power of one core, of 1 square meter of your processor doubles in 1.5 to 2 years. Yeah, so basically if you wait 2 years, then you have 1 square centimeter processor with a double as high performance as it was 2 years before. And that's a log scale law. Yeah, so if you wait 4 years, then it's like 2 by 2, 4 times more powerful. If you wait 3 years, and it's not like 2, 2, 2, 6, it's 2 multiplied by 2 multiplied by 2 is 8, yeah, and so on and so forth. And that, and that's actually is a very, very huge rate at which our computational power increases. And what happens to the cost per human genome? It drops down even faster than the Moore's law. Yeah, so technological developments are so rapidly happening in the field. Then you have, as you correctly said, 500 to 600 euros per genome, full reading, and then we should be able to understand, because still we do not understand what genome tells us. Yeah, so we have basically a sequence of 4 letters, but we have to select genes, we have to be able to identify genes, and we have to understand what these genes do in our body, and that is what is still missing. And once this link will be established, because what is going on in our body, but what our genes basically dictate, yeah, and you have also sleeping or hidden genes which are not active, or maybe not active yet. And then if you're able to understand all this genomic picture, then of course you will be able to come with a personalized diagnostic tools and more personalized treatment tools. For example, you have an illness as this Alzheimer disease that can be, so to say, preemptive treatments prescribed for you. So you take, for example, pills at the age of 50 and not to get this Alzheimer disease at the age of 65, for example. And then, of course, in Europe, there is impeded by the personal data storage, but I think is, to be honest, is a temporary problem. So usually people in Europe especially are very sensitive to the personal data. And then, of course, we have to find solutions which can accumulate safely and store and analyze the most personal data you have, your DNA. You don't have more personal, basically. This is the DNA code, which is at the core of your function, basically. And then I can imagine that many people will be against of reading such sequences, storing them, manipulating with them, and so on and so forth. So that's a huge topic, but that's not about personalized medicine. It's about mindsets. We can discuss this. I had numerous discussions with many people on this. So this is about basically one size fits all is no longer what is going to happen. The second thing, agricultural biotech. So what do we understand by agricultural biotech? So we basically create new plants which contain specific genes which make these plants more stable against pesticides, and which give another features to the plant. For example, if we harvest tomatoes, they have, they are more colorful. They are the plants are more stable against diseases. Actually, that's what many people do not maybe consider when they say, okay, I don't want genetically modified something. But we have a huge problem. We use a lot of land for like growing plants, but plants unfortunately are also have their own diseases, and then we basically harvest much less than we can or we could because of these plant diseases. And it's a huge actual issue not to use pesticides, but make our plants more robust against those diseases. This is one aspect. Another aspect is to make our plants having features which eliminate further subsequent steps. For example, in this article in Forbes, there was a great example, basically decaffeinated coffee beans. Basically, coffee tree gives you beans which contain almost no caffeine. So then you don't need to apply decaffeination process, which is usually done basically with organic solvents. Yeah, so you extract coffee at mild conditions and the mild temperature and pressure, but often you use organic solvents like ethyl acetate, for example. Then you have to, with the steam, get rid of this ethyl acetate. Then, of course, it all costs you energy and all costs you waste water, and organic solvent is not remaining inside. Don't worry about that much. So the certification and regulations, at least in the European Union, are way too strict to allow any acetonitrile or any other organic solvent to remain after the extraction. But nevertheless, I mean, you basically use a lot of energy for this as well. Why not to create such plants? This is all about agricultural biotech vision. That's what is going to be developed. And again, I have to admit, unfortunately, not in the conservative European countries. So here, more towards Asia, more towards countries which want to experiment, and then they put pressure in terms of cheaper crops, for example. But that's again a little bit of political discussion, which we are not going to enter. The third thing which this Forbes article mentions is extremely important. This is fast pharmaceutical testing and approval of medicine. The picture which I taken from EMA, European Medical Agency. So they have a nice webpage on COVID-19 development and evaluation and approval, but this scheme is applicable to basically every and each drug. You have from R&D, from very small scale in vitro studies, basically in a test tube, all the way to the safety studies. Then commercial manufacturing the real commercial manufacturing actually begins somewhere here. Yeah. This way takes approximately 10 years. Big pharma invests a lot of money here and here, and also in clinical trials, and then you have non-zero probability that you fail at one of these steps. It means that all your effort have to be start from the beginning. So your lead, your candidate for the drug, for example, turns out to be very toxic when you do clinical trials, and then you stop clinical trials. So you never go to evaluation, to decisions, which are done by FDA in the States and European Medical Agency in the Europe. Then, of course, you don't plan any industrial production. What has happened with the COVID-19, of course, we had to react very, very fast, and that's how the new scheme, new timelines look like for COVID-19. I'm impressed by this picture a lot, because look how all these phases, which you just saw in the previous picture, are getting compressed, and basically many things are where there is not that much gap between vaccine available for use and all the steps. Pharmaceutical quality and non-clinical research, yeah, so is going on almost together with the clinical trials of the phase 1 and 2. And then the authorization and scientific evaluation, that's what authorities basically, FDA, EMA do, also begins in the middle of the phase 1. That's possible. Take a look at the conventional picture. Yeah, phase 1, just pharmacology studies. You basically have only at this point, you have only pictures for rats and pigs, maybe for rabbits, something like this. So you, of course, you have done your in vivo studies, but then where did the first trials under hospital conditions in clinics begin? Of course, it's way too early to think about any authorization here. Yeah, so it's going to be in the conventional scheme, I don't know, maybe 5 years or something like this. It depends, of course, on the disease, on how many cases you can collect, how well your clinical trials are designed, but it's a huge amount of time. With the COVID-19 vaccines, we had no time, and that's actually demonstrated that we can compress all these steps. We can also do studies after authorization once the scientific evaluation has been done. That's basically maybe in real life. Actually, there's also a gap here, because large scale production is shifted to the right, because basically large scale production waits a little bit until the authorization is done, and then once the large scale production starts, then you have basically your drug tested on many people. That's the thing which demonstrated basically that we can be very fast. It demonstrated that we can rely on big technological companies, on digitalization, on our previous experience, and we don't need to start everything from scratch, and we have to basically not treat every and each drug as a newcomer, but we have to take all our experience and build upon this basically. Plus, what also important is that we are now able, and I'm going to show you in a second, we are now going to understand much better how drugs interact with our body, because this is the main issue, why we have a big or a very low probability that the drug candidate, better to say, over here reaches the large scale production, because basically we just take, of course, we have many tests and we have many knowledge, but at the end we do not understand whether this drug is going to be toxic. The simple reason for this, we can't predict toxicity very well, and if we can, then we just seed them out at the earlier stages. We don't let this drug candidate go to the clinical trials. We say, okay, let us chemically modify this drug to be less toxic, and to interact with a specific protein, not to be involved in a specific pathway in our body. And that's actually can all be done, people say now, in silico, in vivo, in vitro. In vitro is basically on the table, and in lab. In vivo, body, also human body including. So for example, you take a pill, and then blood is analyzed after, say, half an hour, 2 hours, 3 hours, and so on, and people construct how large the concentration of a particular drug in your blood as a function of time. And then what they analyze, what is the highest concentration, what are the safety limits, and so on. Basically, you don't have disease. This drug is for, but that's what we can also do, not in vivo now, but in silico, having extremely high computational power and well understanding of what is really going on in our body. So basically, we are on the way to create a digital clone, yeah, a digital model of the body, and then personalized medicine hopefully will come on top, and then it will be not just an averaged human body or organism, yeah, but all the systems, but your personal, because now it is impossible, yeah. And then the drug will be prepared for you on demand, so to say, yeah. So we know this drug is safe, but for example, you have a special type of allergy, and then you say, okay, my doctor automatically just screens your genome and say, okay, you have a specific gene, so you're going to have allergy against this drug, and then this drug is going to be modified, and a small company produces and delivers this, and you take it. Yeah, this is a real personalized medicine. And all the tests are not, because now it's impossible. Yeah, if you want to create a design drug, then you basically have to slightly modify. You have to go once again all the steps to get certification, to get an approval from officials. And if these steps can be done in a shorter time, then you have a chance to get your personalized, real personalized medicine. That's very interesting. That's going to happen, I hope, before we all retire. What else? Let us quickly discuss two more things. Environmental biotechnology. Well, I mean, this is mainly about environmental degradation of plastic and waste. Yeah, so we are now much better understand how plastics degrade, and we of course have to find a way how to break down synthetic molecules with biological, not like burning them now and producing more CO2. And this is, again, is extremely big topic, and many companies are now on the way to find more robust, more stable enzymes, because you can imagine, yes, such pictures like this, they always show a very, very clear picture. You have like pure water and a few plastic PET bottles like floating there. Is not true. Yeah, you know how the like garbage basically looks like. So that's all possible contaminants, and what you're gonna have here is a extremely complex mixture, and your enzyme has to still work and destroy plastic, no matter what kind of heavy metals, I don't know, I mean, what else, food residuals and so on are present in the fermenter. Detergents is also a big thing, yeah. So I don't know whether you know or not. Basically all our soaps, or most of our soaps and detergents now, not in industry, also just in common use, contain enzymes. Basically enzymes, cleavage, the analytic style, some contaminants, and that's what is a big thing to basically develop more stable enzymes for such detergents, and to make them basically washing compounds or formulations for washing, for cleaning, more biodegradable. That's of course also an issue. Something else, I think really know, and this is the last slide I have here, so-called cultured artificial meat. For those who do not want to switch to vegan diet, and at the same time understand how much water and how much agrochemicals we require to produce 1 kilogram of meat. It's actually very well fits to our discussion with insulin. Yeah, and we need by a factor of 20, 50, 100 more water to produce 1 kilogram of meat. And that's, of course, then represents a big thing. The second thing is food shortage. So for those countries where we have issues, you know, I mean, starvation basically, millions of people on earth, they don't receive food. And this is responsibility of the developed world to offer solutions for this. And this cultured meat is all not only about vegan diet and all these fancy things. This is actually poses a much more important question: whether we can produce food using less resources on a 1 square meter instead of on a field, using basically very little amount of water and snow, or very little amount of chemicals. And that's all central questions behind this artificial or cultured meats. Yeah, so this particular picture I'm just taking from a very recent and very nice review in Nature Food. It tells us that actually to mimic meat is not just enough to grow muscles. Yeah, so it's relatively more difficult task to grow muscle cells on a substrate which is also, you know, edible. The issue is to mimic meat, you have to introduce various cells, and various cells require different conditions for them to grow. And if you really want to mimic meat, you have to have you know, various cells which support, for example, muscle cells and endothelial cells, and they have to grow exactly as they do in our muscles tissues. And if you really can reconstruct such a process, and you can create matrices which very closely mimic and simulate the tissue structure, and then you grow basically this all types of cells on this artificial scaffold, if you will, then you get real artificial meat. All the solutions currently available are kind of, you know, closer to going closer and approaching close to this state, but not fully. This is a vision for the next, say, you know, 5 years or something like this. But again, the big question behind this all is risk of starvation and use less resources to produce foodstuff. I hope that you're going to have during your professional career chance to work in one of these directions or in directions which just emerge. I thank you all for attending the lectures. I hope was, although it was maybe difficult exercise to go through all the material we just discussed. I hope you enjoyed as I enjoyed this. If you have questions, this is, I think, time to ask. If not, then we see each other on 24th, the final presentation, of course, and the final exam, and also consultation hours offered before the final exam. We're all available to an extent, and wish you good luck with all your other exams. Thank you, and really wish you good luck. Goodbye.
Thank you.
Thank you. Have a nice day.
Thank you.
Have a nice day. Goodbye.